Chapter 25, Statistical Thermodynamics, Section 25.3, Rotational partition function and energy. The average rotational energy can be determined given the rotational partition function using the following equations. The average energy is equal to negative d ln q over d beta. The average energy is kbt squared d ln q over dt, or kb times t times d ln q over d ln t. If we use the rotational partition function here, we'll get the average rotational energy. For the three-dimensional rotation of a linear molecule, such as H2, HCl, and HCN, the rotational energy levels are J times J plus 1 times H bar squared over 2I. J can be 0, 1, 2, 3, etc. For a diatomic molecule, I, the moment of inertia is mu times R naught squared. Mu is the reduced mass. 1 over mu is 1 over m1 plus 1 over m2. For a linear polyatomic molecule, I is the sum of mi Ri squared. Here R sub I is the distance between the mass m sub I and the center of mass of the molecule. The rotational partition function for a linear molecule is the sum of 2j plus 1 times this exponential function e to the power of negative j times j plus 1 times h bar squared over 2I over kbt. Or it can be written as the sum of 2j plus 1 times e to the power of negative j times j plus 1 times h bar squared over 2I kbt. I just placed this 2I on the bottom. J is the rotational quantum number. J can be from 0 to infinity. The degeneracy of the jth rotational energy level is 2j plus 1, because the z component quantum number, m sub j, can adopt 2j plus 1 different values. M sub j can be negative j plus 1, etc., all the way to j. Again, the rotational partition function of a linear molecule is the sum of 2j plus 1 times e to the power of negative rotational energy over kbt, or j times j plus 1 times h bar squared over 2I divided by 2 kbt. It's extremely difficult to get the sum right, so we make an approximation here. We assume this integral of the same function is equal to the sum over here. We have this rotational partition function of a linear molecule approximately equal to the integral of 2j plus 1 times e to the power of negative rotational energy over kbt dj. J is from 0 to infinity. We will simplify this integral by doing variable substitution. We can set x to be j squared plus j. Therefore, dx is simply 2j plus 1 times dj. And we do see 2j plus 1 times dj here. That becomes dx. And on top, j times j plus 1 becomes x. Since j is from 0 to infinity, x should also be from 0 to infinity. So we have this integral here. It's not simple enough. We now set z to be h bar squared times x over 2I kbt. And then this function becomes e to the power of negative z. Meanwhile, x is 2I kbt over h bar squared times z. Therefore, the rotational partition function of a linear molecule becomes this 2I kbt over h bar squared times the integral of e to the power of negative z dz. And z is also from 0 to infinity. The integral of e to the power of negative z is negative e to the power of negative z. We can plug in infinity and 0, take the difference. The result is 2i kBt over h bar squared. Or we can write this as kBt over h bar squared over 2i. And remember, we defined this rotational constant in a way that hcb is equal to h bar squared over 2i. So the rotational partition function for a linear molecule can also be written as kBt over hcb, only because we defined b so that hcb is equal to h bar squared over 2i. Again, hcb is equal to h bar squared over 2i. B is the rotational constant. B is h bar squared over 2i over hc, or h over 8 pi squared ci. C is the speed of light, I is the moment of inertia, and h is the Planck constant. After the inversion symmetry of the linear molecule is considered, the rotational partition function of a linear molecule should be kBt over sigma hcb. So what is this sigma? It's the symmetry number. For a linear molecule with an inversion center, such as H2, sigma is 2, because of the indistinguishability of the rotation of the molecule at 0 degrees and 180 degrees. For linear molecules without an inversion center, such as HCN, sigma is just 1. So if we look at a linear molecule, it belongs to either D infinite H point group or C infinite V point group. If it's D infinite H, sigma is 2. If it's C infinite V, sigma is 1. We have the symmetry numbers for different point groups. If we have a point group C1, Ci, Cs, or C infinite V, sigma is 1. When we have rotational axis Cn, Cnv, Cnh, sigma is n. For D infinite H point group, sigma is 2, because if you rotate H2 180 degrees, you will get exactly the same configuration. For Dn, Dnh, Dnd, sigma is also 2n, 2 times this. Some higher symmetry point groups. For T or TD point group, sigma is 12. For OH point group, sigma is 24. For IH axohedral point group, sigma is 60. Finally, this S2n point group, sigma is n. For example, when we study the homonuclear diatomic molecules or any other linear molecules that belong to D infinite H point group, we must consider the fact that rotation about 180 degrees simply interchanges two equivalent nuclei. That means no difference, because the new orientation is indistinguishable from the original orientation. We must divide the rotational partition function by 2. Sigma is 2, so that indistinguishable orientations are counted as only one correctly. For heteronuclear diatomic molecules or any other linear molecules that belong to C infinity V point group, rotation by 180 degrees produces a different orientation. Therefore, sigma is just 1. We do not have to make any corrections regarding symmetry. In CH4, if we allow free rotation of the hydrogen atoms, there are 12 possible arrangements or orientations. Therefore, sigma is 12. And this is because when the 4 hydrogen atoms are labeled, there are actually 4 factorial, which is 24 different permutations. But among this 24 permutations, for the 4 labeled hydrogen atoms, for example A, B, C, and D, half of them, that means 12 permutations, are identical via rotations and should be counted as just one. The other half of the 24 permutations are the enantiomers of the first 12. So this 12 is considered just one orientation, and this 12 are considered another orientation. The rotational partition function of a linear molecule is this: kBt over sigma hCb. Sigma is the symmetry factor. Now we're going to look at the average rotational energy for a linear molecule. It's going to be kBt squared d ln q over dt, and this q is the rotational partition function for a linear molecule. We plug in the expression over here. Q is kBt over sigma hCb, and this is logarithm, so we can separate this logarithm into 2 different logarithms. One contains temperature, the other does not. This part does not depend on temperature, therefore we just need to evaluate d ln t over dt, that's 1 over t, and then the final result is simply kBt. For a linear molecule, the average rotational energy is simply kBt. The molar rotational energy is simply RT, because Kb times the Avogadro constant is R. Without showing the proof, the rotational partition function for a nonlinear molecule is this. We have a constant here, the square root of pi over sigma, and then multiplied by kBt over hCb1 to the power 1/2, kBt over hCb2 to the power 1/2, kBt over hCb3 to the power 1/2. B1, B2, and B3 are the 3-dimensional rotational constants. And this whole thing can be written as a constant times t to the power 1.5, because we have t to the power of 1/2, t to the power 1/2, t to the power 1/2, 3 times. So everything else becomes this constant c. And then we have t to the power 1.5. That's the rotational partition function for a nonlinear molecule. Now let's look at the average rotational energy of a nonlinear molecule. Again, we just need to do this kBt squared d ln q over dt. Ln q is ln c, the constant, plus the logarithm of t to the power 1.5. And ln c does not depend on t. Over here we have 1.5 times d ln t over dt, which is 1 over t. Now the result is 1.5 kBt. The molar rotational energy is 1.5 RT, because Kb times the Avogadro constant is R. Why 1.5? So when we are looking at 3-dimensional rotation of nonlinear molecules, the rotation can be done about the x, y, and z axis. So for the rotation about each axis, the average energy is 1/2 kBt. And we have 3 of them, therefore we have 1.5 kBt. For a linear molecule, assuming the molecular axis is the z-axis, then we have rotations about only the x and y axis. The rotation about x is 1/2 kBt. About the y-axis, also 1/2 kBt. So we sum up these 2 1/2 kBts. We get 1 whole kBt over here for the rotation of a linear molecule.